My name is Esad, and I am a postdoc in Mining and Mineral Engineering Department at Virginia Tech. I'm working in Dr. Sarver's group. This presentation will deliver information about rapid silica analysis by direct filter FTIR.
Before we get into the details, I would like to give you an overview of the structure of today's presentation. These headers in the following table of contents slide have hyperlinks for you to go to the slide easily and quickly. Just press Ctrl and click on whatever section you want to proceed. We will begin with some acknowledgements and a list of additional references. Then I will share some key background information related to this analysis. After that, we move into sampling materials and equipment, where I will explain the setup, the sampling train system, and so on. Next, we will go into the DOF FTIR analysis. In this section, I will walk you through software startup, baseline, and sample measurements, and I will show you how we get the spectra, how we run the macros for silica analysis, and generate reports. Following this, we will cover creating a site-specific calibration factor. That includes developing a site-specific data set, obtaining data model equation, and applying the calibration curve to your own field sample. Finally, we will end with quality assurance and quality control to make sure everything we have discussed is validated and reliable. And just as a note, at the bottom of each slide, you will notice a little note that says return to contents. They are also hyperlinked. When you press Ctrl and click on it, it will take you back to this table of contents slide.
This presentation has been created as part of the project Evaluation of Micro-Respirable Silica Monitoring Tools for the Aggregates Industry, which is funded by the Alpha Foundation for the Improvement of Mine Safety and Health. The rapid silica analysis method discussed here was originally developed by CDC NIOSH. For more information, please consult the references on the following slide. Note there may be multiple options for the sampling and analytical hardware required for the rapid silica analysis method. Mention or demonstration of specific options here does not imply endorsement of any specific vendor or manufacturer. This slide simply lists some additional references. These are studies that provide more background and validation for the methods we have discussed here in this presentation.
Respirable crystalline silica, known as RCS, is an occupational health hazard in many mining environments. As such, there is strong interest in tools which enable monitoring measurements to be conducted rapidly and frequently. There are multiple RCS minerals, including quartz, cristobalite, and tridymite. In many mining environments, quartz is a predominant RCS mineral, and alpha quartz is a thermodynamically stable form. The rapid silica analysis method discussed here utilizes direct on-filter sample Fourier transform infrared, known as DOF FTIR, spectroscopy to estimate the mass of alpha quartz. In essence, filter samples are collected using the same equipment and procedures as would be used for traditional, that is, compliance sampling. However, the filter can be directly analyzed without special sample preparation requirements, hence the rapid descriptor. Moreover, if a portable FTIR instrument is used, the analysis can be completed at end of shift. The rapid silica analysis method is not currently accepted for demonstrating compliance with US regulations. However, under certain conditions, it may be useful for a variety of non-regulatory purposes, such as engineering studies of dust sources and controls, or tracking trends related to mining practices, geology, or environmental factors. To use this method, a site-specific approach is recommended to account for the local geology. This can help to first understand whether alpha quartz can serve as a suitable proxy for RCS, and second, evaluate the possibility of non-quartz mineral interference with the FTIR response attributed to alpha quartz. A site-specific approach necessarily entails initial and then periodic analysis of filter samples by an accepted reference method, such as NIOSH method 7500. This enables determination of the presence of RCS minerals other than alpha quartz. Thus, the site can evaluate the extent to which alpha quartz can serve as a suitable proxy for RCS. Assessment of the correlation between FTIR results and true RCS mass. An inconsistent correlation could be due to the presence of minerals which interfere with the FTIR response or problems with the sampling or FTIR analysis procedures.
I will first introduce the basic sampling materials, and then the presentation goes from there to the sampling procedure using the analytical methods. And then I will deliver some information about creating the calibration curve and then applying this curve to your own samples. Then finally, the quality control for your results.
Samples are collected with escort elf pumps operated at 1.7 liter per minute and 10 millimeter nylons cyclones. And we use Provate 37 millimeter polyvinyl chloride filters, 5 micrometer nominal pore size in 3-piece string cassettes. And it is recommended to use preloaded and Provate cassettes to ensure a proper seal and making it easier to find the sample weight if needed. These parts are what we need to set up a sampler assembly. This setup is used to collect respirable dust samples in occupational environments. So the escort elf pump on the left draws air through the sampling train at a controlled flow rate, which is 1.7 liter per minute for aggregates. And the sampling train components here in the middle, tubing connects the pump and the cyclone and filter cassette. The cyclone separates large particles, allowing only respirable size dust to reach the filter by centrifugal action. And those cyclone brackets and clips secure the cyclone to the fixed locations, and the other adapters and fittings ensure airtight connections between the cyclone, filter, and tubing. Here's a video. This video and next few videos demonstrate the assembly of the sampler components step by step. Each part is securely placed to form the complete sampling train. This assembly will take the cassette on the top of it in the next step. An important point on the cassette, both sides will say either inlet, here it says inlet, the flat surface, or the outlet. Here it says the outlet, wagon shape surface, which are critical locations for doing the correct pump connection. And then you will want the inlet side facing down on top of the adapter, and the outlet will be at the top. The wagon shape outlet will be at the top. This is very critical for
the correct sampling. Now it's time to make the cassette and terrain connections. After you take the caps off from the cassette, the wagon-shaped surface, the outlet surface, will be positioned on the top, and the flat side inlet will face down to the cyclone. Push the cassette firmly until the coupler between the cyclone and cassette completely gets it inside, and then place the top of the sampling train and make the back screw of the sampling train hand tight. We then make the connection between sample and the pump using the vinyl tubing. And the pump is now ready to start whenever you are ready to do the sampling. We will adjust the pump to run at 1.7 liter per minute, and the pump reaches the desired level, usually in seconds. After the sampling done, we will stop the pump, take this cassette out, and plug the caps into inlet and outlet sides of the cassette. And once we get into the lab, we take these caps out and take the filter out for the FTIR analysis. Sample collected on PVC filter is analyzed by DOF FTIR to determine quartz mass per the method, standardized by NIOSH, and then mass concentration can also be determined using the sampling flow rate and recording sampling duration. In this work, we are doing the DOF FTIR using an alpha 2 compact FTIR spectrometer and the associated OPUS software. Notably, the OPUS software is used to output relevant spectral peak areas that should correlate to the quartz mass. There are other portable spectrometers available with their own softwares. We are just demonstrating with Bruker's Alpha 2 spectrometer and the OPUS software. So when we mentioned OPUS software on this demonstration, if you're using a different instrument, you can substitute that with whatever software you're using. Next, you will need a laptop computer, and thoroughly the sample cassette cradle base designs can be found, the link here below. The 3D printing components are free. And also NIOSH has developed a free software for coal mine samples called the Field Analysis of Silica tool, known as FAST, for simple processing of the OPUS spectral data to yield a quartz mass value. Since it is not meant for non-coal mines, we will not go over on that in this presentation. Here's a video showing how to go through the OPUS procedure. So to start, you will open the OPUS software on startup. Some initial tests and diagnostics will run. In the bottom right there will be a circle. There will be a circle and it can be gray, means non-connection with the instrument. Red, meaning internal diagnostics find a crucial error. Yellow means humidity warning or expired PQ or EQQ test. Or green, which is great to go. So we will click on that yellow circle and check to see if one of those measurements expired. If so, open and run the expired tests, and it should pop up some web pages, and it should say all tests pass it, and then you will be good to go. And check the relative humidity to make sure that it is below 30%. If it is not, you need to replace or regenerate the internal desiccant pack in an oven at 120 Fahrenheit for 15 minutes. For the gray and red dots, you will need to troubleshoot to fix this issue and consider using the equipment manual or reaching out to the manufacturer. When it is green, as I said, it means we're good to proceed with the analysis. So first, we need to create a baseline by taking a background analysis with a blank filter scan. So for the FTIR scans, we're using this 4 pieces cassettes, black cassettes. Second ring is as a top portion, and third piece with a metal filter support. After we take the pieces apart, we take a blank PVC filter and placing it in the black cassette, and then inserting the cassette into the cradle. And then load the blank filter into the FTIR instrument. Best practice is looking at the blank filter to make sure there is no contaminants visible on it, such as hair, dirt, etc. Here's another video showing creating a baseline by taking a background analysis using OPUS software. Once all the internal tests are complete and you insert the blank filter into the device, open the measurement window on the OPUS software by clicking this Advanced Data Collection button. Click the background single channel button. It will scan the filter 16 times, and then at the bottom you see says no active tasks. So it means it is finished. Now carefully remove the blank filter from the instrument. Here we are starting the actual sample analysis. So we are again using this same 4 pieces cassettes with metal filter support on it. After we have only a bottom compartment of the 3 pieces cassette in our hand, we take our actual dust sample filter. So you open the top pieces out, and you can use a sharp edge tweezer through the outlet hole at the bottom of the sample cassette and push gently from the cellulose pad just to give the filter a bit height. You will need to separate the filter from cellulose pad and then take only the filter, not the cellulose pad, out using another flat edge tweezer, touching very gentle on the surface of filter on the edge as much as possible, and placing it in the black cassette, and then inserting the cassette in the cradle. So we are ready to load this filter into the FTIR instrument. A quick reminder, when you are removing or inserting a filter that has dust on it, you want to be very careful not to shaking your dust off of it. Otherwise you will lose some data. This video is showing how to do the actual analysis using OPUS software. Open the measurement window by clicking the Advanced Data Collection button here in the green tubing button. Once the filter is loaded into the instrument, click the Single Channel Analysis button. Click this Advanced Data Collection button and then Single Channel Analysis button. After 16 scans, it will give the spectra from this measurement, both baseline and this measurement taking less than a minute. So here we have the spectrum. Then we will take our sample out from the instrument and put it back into the original cassette. And again, you want to be very careful not to shaking your dust off of it. So there should now be a graph and a file name under the OPUS browser. Under the scan name, there should be some squares to toggle different graphs. So RSC here is the reference scan, just the empty filter. And SSC is the sample scan contains dust and filter. AB is the difference between SSC and RSC, just the dust absorbance spectra. We need to form the OPUS baseline corrections in the integration. So to do this on the current working display under the OPUS browser, select just the AB spectra. And save this to the scans. Save this to the scans folder on your computer and add to the name to make easily and uniquely identifiable. Have a separate scans backup folder. The first 7 numbers are automatically generated by the instrument, so this can be used to locate the original unaltered scan. Next, the baseline corrections and integration must be run. To do this, we will click the Run Macro button, then find the appropriate file. For us, it is the silica.mtx file. Click Continue, and as you can see, the integration there is colored in for the range. The micro files can be found at this link. Here, you can get them from for each of your FTIR brand and in feature updates. So now we need to generate a report. So to do that, we will click the Analysis Report Generation button here, and then select that scan which we want in the report. Select the template file and then open the appropriate report template. For us, it is the silica_report.art file. And click the Output tab. Make sure the output to CSV file option is checked. And then name your report and click Select Path and select where you want this to be saved. Then click Generate. So now we need to go find that CSV file and do a little editing. And since I generated the report to the desktop, we'll see that here. So all these are just in a single column. Here they need to be spread out until they are each individual cells. So we will select that column first, column A. Find the text columns button under the Data tab, and click that button. And do the delimited, and they are delimited by semicolons, so we can check that semicolon and click Next, and then click Finish. The results column now has the peak area information for quartz in the first row, kaolinite in the second row, and the remaining rows are for muscovite, dolomite, and calcite respectively. And then repeat these steps of sample single channel scans until all the samples are scanned, and generate reports for each sample you analyzed. Create your site-specific calibration factor. You will need to collect a sufficient amount of representative samples in your field. You should collect at least 10 filters that you will use to build your calibration curve. These filters can be collected on different days in different locations, and also aim for a range of sample masses. All these are to ensure realistic and reliable results. These samples will first be analyzed using FTIR. After obtaining your peak area results from OPUS software as explained previously, you will send them to a certified laboratory for standard RCS analysis.
such as Naish method 7500, to get the RCS masses in your sample. And then you will create your mine-specific calibration curve using RCS masses on the x-axis and FTIR QPA results on y-axis. And I will show you how to do that in the next slides. If you are interested in the RCS concentration of your samples, you will also need to record the sampling duration and pump flow rate.
In this video, I will show you how to create your mine-specific calibration factor. You will need a base spreadsheet like this, and you will need to fill this spreadsheet with your QPA value from FTIR and RCS mass values from the external lab. Use sample previously and send them off to a certified lab for 7500 analysis to get your RCS mass values from your sample. And you will need to plot this graph here with QPA values as y-axis and RCS mass values as x-axis. And then the trend line equation of this curve will be the calibration curve you will use in your future sampling. As I mentioned previously, this is FTIR analysis result document, and when we look at the results column here, the first row is your QPA value. So copy that value for each of your sample from these report and come back here and paste it to the corresponding cells in your main data analysis document. And do this for all your samples FTIR results. After taking your results from FTIR to the main document, you will need to start including results from certified laboratory. And after receiving your laboratory results, you will use these RCS mass data to start generating your own calibration factor process. So just copy those RCS masses from results document to the main data analysis document here in this column. And as we are interested in micrograms instead of milligrams, we can use this conversion from milligram to microgram and create this column D as well. Once we are done with data importing from your FTIR analysis results and certified labs RCS mass results to the main datasheet, these QPA values will be your y-axis, and put the RCS mass results, the microgram conversions on the x-axis. You want a trend line that shows some scatter, but demonstrates a clear linear trend. Remember, the more scatter you have, the more measurement error you can expect. And we are adding a trend line to our plot by hovering up on the plot, and from the plus sign, we are selecting the trend line and to get the equation of your linear model, select formatting trend line, and then check the display the equation selection. You can also see the R-square value here to validate your model statistically. Once you generate the trend line and obtain the equation, this becomes your calibration factor. You can use this model in your future analysis results without sending every filter for laboratory validation. The model equation is actually consisting of slope and intersection, and this coefficient of x is the slope, and the second part of the equation is the intersection. And for ease of use, you can find the slope of the curve in intersection values in separate cells to use them in your final RCS mass function. So slope can be found by typing equal slope of the curve in QPA values selected as Y's and RCS mass micrograms values selected as X's. Similarly, interception can be found by typing equal intercept QPA values as Y's and RCS mass microgram conversion values selected as X's. So far, I explained how to create this curve and obtain the model equation for your mine-specific calibration. And using that equation, you will create this column E. Your function will be like this. It is only doing the math of your trendline equation, leaving the X or RCS mass alone on the left, and replacing all the values in the equation and find the RCS mass for that particular sample. And you will do this for all your samples, or just drag this cell down to the end. And I will make an example in the next slide. After creating the calibration curve, you can conduct non-regulatory field sampling and directly estimate RCS mass. When you collect your next sample, you do this FTIR analysis first, and then you will have this QPA value for that sample. And then you need to apply the trendline formula to find the estimated RCS mass of this new sample. So I will walk through with you on how to apply your mine-specific calibration curve to a new sample. You do this FTIR analysis first. You know, this is our typical FTIR results page. And then you will have QPA value for it in the results column in the first row. And assuming you have already your base data analysis table with all the required values for sample QPAs and RCS masses, and copy that FTIR result of the new sample to your data analysis table. And then apply the trendline formula to find the estimated RCS mass for this new sample. And that's it. This yellow highlighted row is our new example sample. We are assuming that we haven't sent it off for RCS mass analysis, but we did the FTIR analysis for that particular sample and calculate the estimated RCS mass by applying this site-specific trendline equation that we just found. So I'm copying that sample 11's QPA value to this table, and in the column in this row, you will see your new sample's QPA mass calculated using the mine-specific calibration factor here. These equations here are telling the story of this function here in this cell working. For this instance, if your calibration factor equation is this, and your QPA is 0.42, replacing every known values in this equation and leaving the X, the RCS mass, alone on the left-hand side of the equation, and do the math on the right-hand side, you will find the RCS mass for the particular sample. And the Excel functions here prepared for you are already doing this math for you. You only need to enter the QPA value from FTIR analysis, and that's it. So this 71 microgram is your estimated RCS mass. In your future sampling, you can apply this equation to your FTIR result to estimate RCS mass and concentration. And it will reduce the need for external lab analysis. There is one more important thing I would like to highlight about the calibration curve. The curve technically covers from 0 to 500 micrograms in my example. However, the upper part of that range is not realistic for personal exposure measurement, even over a full 10-hour shift. That's why when you create your own site-specific calibration factor, you should design this to cover the range that is actually realistic for your operation. Another thing to keep in mind, if you include 1 or 2 data points that are very far away from the rest, they can completely dominate your regression statistics. Hypothetically, your R-squared value might look very good, close to 1, but that's only because single outlier point is controlling the regression. So it is much better to build your calibration using data points within a realistic range for your mine site, and also are evenly spaced across that wider range. Of course, if you're doing some engineering studies that push into higher concentrations, then of course, just make sure your points are evenly spaced across that wider range and could go up to really high concentrations.
Lastly, you should develop a quality control and assurance plan. With this technique, you save considerable amount of your analysis cost, but you still verify your results. Following initial effort to generate a site-specific calibration, it is recommended to send one filter to a certified lab for reference analysis, such as NIOSH method 7500, for every 10 filters you collect, and compare the results with your calibration curve, current calibration curve. You would want to check whether the lab results still fit the calibration curve, and if there are any significant deviations, and use this lab results to update and improve your calibration curve over time. If your calibration curve is changing over time, possible issues could include problems with the FTIR instrument, or changes in local geology, or pump flow rate not properly calibrated. In order for maintaining data integrity, our suggestion would be for every 10 filters you collect, send off an extra sample for quality control. This helps you maintain a consistent check on your data quality. If you start getting results that don't seem reasonable, do not accept them without verification, and always verify unexpected results in your filters for external analysis and review your procedures. Remember, this process is not a substitute for exact data interpretation. You still need to carefully evaluate and think critically about your results. We hope this presentation has been useful to demonstrate the rapid silica analysis method using a portable FTIR instrument on mine samples. We will share the Excel file with all the example tabs so that you can get help from those calculations. If you have any questions or comments, you can reach us at the emails below. Thank you very much.